Hello! In this video, we are going to prove the following theorem. Suppose Zn is a sequence of complex numbers, and suppose Z is a complex number. If Zn converges to Z, then the sequence of conjugates converges to the conjugate of Z. Now, by definition of the limit of a sequence, to say that Zn converges to Z means the following. It means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of Zn minus Z is less than epsilon. And to say that the sequence of conjugates converges to the conjugate of Z means the following. It means for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of the conjugate of Zn minus the conjugate of Z is less than epsilon. Now, in proving this, it might be useful to know some facts about the complex conjugate. And so we're going to be using the following facts in our proof. The first fact is that for all complex numbers A, the absolute value of A is equal to the absolute value of the conjugate of A. The second fact is that for all complex numbers A and B, the conjugate of A minus B is equal to the conjugate of A minus the conjugate of B. Okay, so now let's get into proving this theorem. Now really, we're trying to prove if Zn converges to Z, then the sequence of complex conjugates converges to the conjugate of Z. So to prove that, let's suppose Zn converges to Z. From here, the whole goal is to prove that the sequence of complex conjugates converges to the conjugate of Z, which means we want to prove that this second statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer such that this is true. How do we do that? Well, since we know that Zn converges to Z, this means we are given that this first statement is true. And this first statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we just introduced into our proof. So taking this positive number to be the epsilon in our proof, we have that there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of Zn minus Z is less than epsilon. And the claim is, if we take this positive integer to be the capital N in our proof, then this statement will be true. So, taking this positive integer to be the capital N in our proof, we proceed to prove that this statement is true. And since we're trying to prove a statement about all n greater than or equal to capital N, let's give ourselves an arbitrary n greater than or equal to capital N. From here, we want to prove that this inequality is true. So let's start out by writing the left-hand side. And now, using the second fact about complex conjugates, we know that this guy is equal to this. But then using the first property about complex conjugates, well, this guy is just equal to this. But then notice, we know that this statement is true, right? This statement works for all n greater than or equal to capital N. So in particular, it must work for the n we have here. So taking n to be the n we have here, we have that absolute value of Zn minus Z is less than epsilon. So this guy is less than epsilon. And so we have shown that the absolute value of Zn conjugate minus the Z conjugate is less than epsilon, which is exactly what we wanted to show. And so we have proven this statement, which means we have proven this limit. And so this completes the proof. And so yeah, that's pretty much it for this video.